Good evening, everyone, and welcome to our Phase 1 Grid Implementation Seminar. This is brought to you by Power and Energy Society. This is part one of a two-part seminar for you guys. And really why we created this seminar is just to give those who have no familiarity with power at all or the principles behind it, just to try to get you guys up to speed and help you understand a little bit more. One of the nice things is we kind of take this from a beginner's point of view. Not that any of you are beginners by any means, but you guys have probably heard of many of these principles, and it's kind of like we've become so used to hearing these things that sometimes we don't look any further into them. So today we're here to kind of show you guys the basics of power and talk about three topics today, which I will elaborate right now. So we will be talking about the creation of power, how we distribute it, as well as the generation of power. So then, whenever we talk about power, we really have to talk about for a more sustainable future, and to talk about how to get to a renewable future is the principles behind it. So we will be presenting over electricity, how power is generated, some of the equipment that's used, as well as we'll go into our power generation methods that you guys are familiar with of hydro, wind, etc., and talk about some principles behind them. And then finally, what is the million-dollar question when it comes to power? So electricity. So we have AC versus DC. So direct current, electrons will flow in one direction at a constant rate or pulsating in one polarity. So one polarity basically means if it's positive, it's always going to be positive. If it's negative, it's always going to be negative. So then if direct current was represented by this blue and red line, even if we were to put it on the opposite side and it were to be negative, that would still be direct current so long as it always stays positive or always stays negative. Even if it's pulsating or changing values a little bit, so long as it is always in the same polarity, then it will always be considered direct current. And then we have alternating current. So alternating current, electrons will flow in both directions without a constant value. And so you'll see alternating current is right here in the green. And then we have variable. Variable typically happens when you have a system that has a malfunction in it, has electrical noise, there's waste, or there's just some inconsistency happening. The power efficiency will drop, causing a variable pulse to happen. So we have direct current, and examples of direct current are your batteries, the power supply to your phones through your phone adapters and the little cubes, and then we also have portable chargers. Now for alternating current, examples of alternating current are what's given inside your outlets inside your homes, as well as use within like gasoline generators that people carry around sometimes in their trucks, or even for emergency situations. So that is AC versus DC. And the reason why I bring this up is because all of our power generation methods produce AC or DC. AC being the most common, DC only about 2 of our power generation methods produce AC, but we'll go on and talk about those later. So now let's talk about kind of the heart of power, our grid, and how we create this. So we have three-phase power. So what is three-phase power? So three-phase power is basically 3 alternating currents being generated. So you have your phase 1, phase 2 right here, and then your green phase 3. And if you'll notice, these are only separated by 1/180th of a second. As far as the phases themselves, and then within the whole time for a period to complete of a wave, it's 1/60th of a second. So that is incredibly fast. And what happens is we have these 3 phases together, and whenever they're going so quickly, then it almost seems that we have that 120 volts almost at any given time. So what happens in this is we shift these to get efficiency, because if we only did one phase, then at any given time we can have maybe our lights flicker, we can have abnormalities within our electrical loads. So we have 3 phases put together, and what happens is when we have these 3 phases put together, we get almost a constant flow that we would not notice or be impeded. And if we were to add just a 4th phase, it really wouldn't provide much more efficiency, considering that these waves are so close together and happen within such short intervals of each other that there really wouldn't be any more gained by adding one more. So we have AC that is delivered to our homes, and it is preferred because there's little energy loss over long distances compared to DC. And then a 3-phase system is used, really just hone it in. It is not anything scary. It's not anything complicated. It's basically we generate one wave, generate a second wave 120 degrees apart, and then a third wave, which we will get to on the next slide and talk about kind of how this is truly generated so that you guys can understand it. So how do we make this three-phase power? So we use two things. We use a rotor and a stator, and we use magnets, as well as some ferrous material. So the rotor is the object on the inside that rotates, as stated by the rotor. And then we have the stator, the object that stays stationary. So the rotor in this case would be this right here, and the stator would be the magnets themselves. Now, three-phase power is generated by placing three sets of identical windings of some magnetic material, or really ferrous material, in 120 degrees from one another on a rotor. So if you'll notice, then we have C1 and C2, then we have B1 and B2, and A1 and A2. So A1 and A2 would produce our first wave. Well, really, any of them can be considered your first, but we'll just say A1 and A2 will create your first wave, then B2 and B1 will create your second wave, and C1 and C2 will create your third wave in the phase. And if you'll notice, they are 120 degrees apart from each other. So you'll see that B1 from C1 is 120 degrees. Then you'll see that A1 from C1 is 120 degrees, because these function as one coil on their own. So that's really how the 120 degree shift affects the power generation. So the stator has magnets for the rotor to interact with and generate an electric field to create this alternating current, or this AC, for us to use. So no matter where you go, you will never, ever, ever get away from generators unless you're talking about solar or thermoelectric generators. But you will always see a rotor and a stator in one way or another. So when it comes to things like hydro as well as hydroelectric as well as wind, we pretty much basically just put a turbine on there and say, all right, go on and spin it, and it spins our rotor within our stator. So the way that they work is a rotor shaft is turned using some means of mechanical energy, whether it be water, whether it be wind, whether it be someone trying to hook up an exercise bike to get some free electricity, then so be it. A magnet will move past a conductor to induce some flow of electricity for us. And the potential difference will be created at the terminals of this rotor and stator. And then finally, so what happens is, looking at it from an overview or from a bigger perspective, power is generated first at our substation using whatever means that we have, and then we go on and send it to these step-up transformers. And the reason why we send it to step-up transformers is step-up transformers basically send our voltage, our AC, to super, super high voltages. And we do that so that we can transmit it over long distances without relatively much loss. Then we have sensors that make sure that everything is fine. We don't have any loss, don't have any issues going on past when we're sending this power out. And then from there, we go all the way back to the wires that travel, and you see these regularly past your home. And then the poles where we have that contain the ground wire, which runs from the ground to above the electrical wires. And then these serve as a good path to return electrons and attracting lightning away from the electrical wires. So, and then we also have our step down transformers. So you'll notice we have our step up that bring our voltages super high. And then we have our step down transformers that convert power to lower voltages to be used within your home. And then in some areas, maybe when you're younger going to a park or whatever, you might have sat on one of these green boxes, and you'll notice these are also transformers. So we use these transformers to be able to bring the electricity down to a usable, and maybe, I'm not going to say completely safe, but safer for our homes to use. Because if you were to have something like this before it was actually stepped down and go through an actual person, it would not be a good story. So the topics that we're going to speak about now that we've gotten the principles out of the way, as well as kind of what equipment and how we use it out of the way, we'll go on and talk about hydroelectric, biomass, wind, natural gas, solar, thermal, as well as the $1 million question. We'll also be talking about sometimes within these power generation methods, the drawbacks on the environment, as well as the effects, and where we will go in the future, or if this is something sustainable for our future. So the first one we have is hydroelectric. So hydroelectric is water stored power, and you'll find out kind of why I say that. So power here is not stored in the form of electricity, but it's stored in the form of water. And we release that water down through the dam, and then it spins a turbine whenever we need it. So basically what happens is you can think of this as kind of a battery. So the water is what we use to power it, and it's how much power we can get out of it. And we basically store it, and whenever we need it, we just pass it through the generator and the turbine to go on and generate that electricity. So in hydroelectric, the power is not stored in the form of electricity. There is no storage that happens here. What basically happens is when we need power, then we go on and send the water down through the dam, and then the turbine spins to send that power to your home, or really to a substation transformer, and then it follows the guidelines that we had set earlier. And then in lulls of power use, so basically when people aren't using as much power, they use that same power that the turbine is creating when the water goes downstream to pump it back upstream as a storage reservoir. And we basically use that whenever we need it. So this produces alternating current as a result of using that generator, the stator and the rotor. And then that's how you get that's how you can get a phase of your AC, because the stator and the rotor will have coils on them, and they'll have those 120 degree shifted coils that'll cause us to be able to create our three-phase power. So next we have biomass. So biomass is by no means a sustainable means of power generation. So materials that are used within creating or using biomass as fuel or for power generation method are wood, wood products, sawdust, firewood, wood chips, crops like corn, soybeans, algae, manure, solid waste like paper, cotton, food waste, and wool. And then we have the actual process that happens where they turn it into some kind of petrol or some type of liquid to burn. So we have pyrolysis, which heats organic material at a certain temperature and in almost oxygen-free space to produce fuels such as charcoal, biofuel, renewable diesel, methane, and hydrogen. One of the things that's kind of funny is we have renewable diesel. So renewable diesel, the reason why we call it renewable, or why they call it renewable, is because we have this thing called carbon intensity. And carbon intensity is measured as the amount of effective carbon emissions per unit of energy that is created. And renewable diesel is created by taking animal fat or spent oil and using it to create this renewable diesel. So we take things that are otherwise would have gone to waste, create diesel out of it, and then whenever we use it, the reason why they say it's renewable is because we can continue to use other things to create it that are already waste products, and then also that the renewable part of it, saying that it's not as harmful to our environment. One of the things about this is the carbon intensity of gasoline is about 110, while renewable diesel is around 50. So with renewable diesel, one of the reasons why they say renewable is because it is 50 to 60% less carbon intensity than gasoline itself. So we also have gasification. So gasification is when we heat materials using controlled amounts of oxygen and or steam to produce a carbon monoxide and hydrogen-rich gas called synthegas. So this is used as fuel for diesel engines, for generating electricity in gas turbines, as well as when further treated, it can be burned within fuel cells. So this is by no means a method for us to pursue in the future. And in any indication that we can say, renewable diesel is maybe a stepping stone for us to decrease our emissions, but ideally we want to get away from creating these emissions and transition out for more sustainable power generation methods. So the next one we have is wind power. So wind power produces AC as well, and what basically happens whenever we produce this AC power using wind turbines is first the wind strength is measured and the blades are faced in that direction just so that we get the optimal amount of wind to create the optimal amount of energy and the most that we can get out of it. But it uses a generator. So we use that turbine and that stator and rotor to be able to create the phases of power that we need, send it to a transformer, and then from there use it within our grid. So one of the cool things about we can use this wind turbine to actually store energy in the form of a mechanical flywheel. So for those of you who have not seen a mechanical flywheel is so amazing. Basically what happens is you have this vacuum sealed kind of container, and floating within it is a magnetically levitated mass. And during the time that the mass is rotating, what happens is there's no air drag within there because it's levitating and it's vacuum sealed. And what they do is they use the power that these power generation methods create, and they cause it to accelerate this mass super, super fast within this container. And whenever they need the power, instead of pushing the mass to rotate even further and further and further and storing this kinetic energy, what they do is instead of turning it into a motor that turns something, they reverse it and they say, okay, let's let that mass spin and let's cause it to create electricity. So it ends up causing a magnetic field, and from there it turns into a generator to release the stored power within it after it gets done using all the kinetic energy that it has, now that it has some field interacting with it. So flywheels are absolutely amazing. You guys should look into them if you have not. On the next power generation method video that we're going to do, I'm actually going to show a small clip that basically shows how they work, but we'll talk about that in a future date. So then we have natural gas. So natural gas is, a lot of people you'll see like UPS has the natural gas cars and things like that. So natural gas, one thing about natural gas is it is not necessarily a sustainable means for us to go in the future, although it does reduce our emissions. One of the things is it is not too far from our other it is not too far gone from our other power generation methods. So if you'll notice inside the top right-hand corner, we have our pounds of CO2 per BTU of a substance, and we have for coal, it's 228.6 parts per million. Then we have gasoline, which is 157.2 parts per million. And we have natural gas ranging in from 117.0 to 139.0. So as you can see from gasoline, this really isn't far too much more efficient. This isn't, as you can tell, it's not too far off from the numbers. If you see gasoline 157.2, the max of natural gas being 139.0, although it has less emissions, this is not somewhere we want to go in the future, but also could be seen as a stepping stone. But truthfully, we want to get to renewables and carbon negativity as soon as possible. So natural gas starts with piping the natural gas underground to power plants. We use the gases methane, ethane, propane, pentane, and butane. Butane is not listed here for those of you who are inclined to know chemistry or have an affinity for it. And then it is commonly used to boil water that becomes steam to drive some kind of turbine and spin that turbine. And this, using natural gas, helps produce alternating current. So the next one we have is solar. Everyone pretty much knows what solar is. Solar was, amazing when we were children. And not a lot of people understand what happens behind solar. They understand the sun hits, a panel of things, and then all of a sudden, bam, electricity. Well, we have stages to that. So the stages that it happens is, one, a photon is absorbed by the photovoltaic cell. So they're called photovoltaic. Those are the cells within the solar panel. And it's made out of some semiconductor, and it generates a flow of electrons. So if you'll notice right here, here is your N-type silicon, which is a semiconductor, and then your P-type silicon. And basically what happens is light energy hits these semiconductors, and then from there it is connected to a load, or maybe it'll be the load is actually to charge a battery, or maybe it's a device to spin some type of small motor, or even to be sent somewhere. And what happens is it shifts the electrons within this. So say you have a battery, then it'll enter to your N-type silicon. It will knock electrons into your battery to constantly charge it, and that's how we get that, because the electrons that are currently separated to their anode and their cathode will now be distributed in the battery in a way that it starts charging. So stage 2, we have the photon strikes a semiconductor material, the silicon, and then it releases electrons from its atoms within the silicon, or from the semiconductor, whichever one that's being used, and it leaves behind a vacant space known as a hole. Then in stage 3, we have that layer that has a surplus of electrons becomes the negative terminal, and the side that has a deficit of electrons becomes the positive terminal. So an electric field is created at the junction between these two layers, and from there we have the diffusion of electrons to either power a device or to charge something. Power generation we have is thermal. So we have two types. We have geothermal, and then we have thermoelectric, which is also known as TEG, T-E-G. So when we use geothermal, a well is drilled into a geothermal reservoir with an injection well drilled to return used fluids to the geothermal reservoir. Then that hot pressurized fluid is allowed to expand rapidly, and it results in mechanical energy that turns a turbine blade, and from there that helps us produce alternating current. Now, this is not available for every state or every region, but for those places that have the advantage of this, they will typically use geothermal as one of their power generation methods. Then we also have thermoelectric. So thermoelectric, what happens in this is we have two different materials. We have one type of metal and another type of metal, and they pass electrons between each other. And we'll go on and talk about that after this, because we'll talk about two really important principles. So these are called TEGs, thermoelectric generators. One of the things about thermoelectric generators is they're only 5 to 8% efficient, and they produce direct current. So within these, they're really not something that we can use to reliably source electricity for us, but they're typically used as a way to recover electricity from something. So say you have some power generation method that is already producing excess heat or something like that, then what you can do is apply this heat to the thermoelectric generator and then get some sort of recovery for that extra heat energy lost in the process. So the way that thermoelectric generators work is by this principle called the Seebeck effect. So the Seebeck effect basically happens when two different metals are exposed to different temperatures or a variance in temperature. And the Seebeck effect applications are the foundation of thermoelectric generators. So they're also called Seebeck generators, which convert heat into electrical energy. So the voltage produced by the thermoelectric generators or Seebeck generators is proportional to the temperature across these two metal junctions. So basically, if you have two different metals, then what happens is if one has a temperature difference, if one is hot, then it'll cause electrons to flow between those two to create some kind of potential difference. And then we also have the Peltier effect. So the Peltier effect is whenever we have two dissimilar metals, if you pass current or you pass electricity through them of these two dissimilar metals, then heat will be absorbed by one of them and then heat will be released by the other. So an example of this is kind of the new refrigerators that are coming out. Rather than using refrigerant, they will use the Peltier effect, which is the opposite of the Seebeck effect. And what happens is one metal becomes super, super hot, one metal becomes super cold, developing even ice on it. And what will happen is if you have one of these new refrigerators, what will happen is, say you go for a midnight snack or something, then you will notice that the back of the refrigerator is hot, or it's blowing hot air to dissipate that heat, while the inside is nice and cool. So one of the things that you might notice is maybe the small little mini fridges within hotels, how they have that one little shelf that's iced over. Then that's an example of the Peltier effect. What they're doing is putting two dissimilar metals. One of them is absorbing all the heat, and then one of them is dissipating all the heat. So an example is that ice can be formed on one end while the other needs to dissipate heat and either blows off heat or has some kind of heat sink on it. And that is the Seebeck and the Peltier effect. So how can we reliably store power generated? In most power generation methods result in alternating current. Alternating current we cannot store unless we rectify and turn into DC, but it's very, very hard for us to change DC back into AC, and is very costly. So we have three things. Is we can, one, rectify the AC power to be DC and store it within flywheels, lithium ion batteries, lead acid batteries by using it to separate the chemicals to their respective anodes and cathodes. Or we have the Harvard flow batteries, which are flow batteries. They consist of two tanks of liquids that feed into electrochemical cells, and they're two chemicals put together, and their capacity is amazing. The only problem with it is the bigger capacity that you need for the battery or to store, the more chemicals you'll need to use within this process, as well as you have to worry about things such as leaking and things like that. But basically, electrons flow between a thin membrane of these electrochemical cells, and it is a very cool thing to look into if you guys haven't. We will elaborate on those in a future video as well. Or three, for us to find a cost-effective way of converting DC to AC. So DC again is that constant or that pulsating wave, and then you have the alternating current, which goes in both polarities. So how do you get something that's constant to now become alternating current, but getting something that is varying, like alternating current, can be done using certain types of circuits to produce DC. So our $1,000,000 question is, how do we reliably store the power generation, how do we reliably store power generated if most power generation methods result in AC? So if you have not found a passion yet, if you want to look into something, this is definitely something to look into, because for a more sustainable future, we want to be able to store the power that we create. One of the things that absolutely blows my mind is every electron that we use with an electrical device, everything that we use has either been put there purposefully by putting two chemicals together in the case of a battery, or by putting those electrons within some device, some storage method. No electrons are just, like freely given in the world unless you're hit by lightning. But it's crazy for me to think that every single electron that we've used within our life has been put there purposefully for us to use, or every piece of electricity that we've used has been purposefully generated for our use. So that is all for our grid implementation seminar part 1. If you guys have any questions, you are more than welcome to reach out to me. For those of you who did use the PDF that basically just has a few questions to outline kind of what you learned during this, then I am very grateful for those of you who decided to fill that out, just because I did want you guys to get a sense, for those of you who are a little bit more hands-on or need something in your hands, to feel like you learned something, that you did truly get that. So I do hope you guys have a wonderful day and be safe.